Hello all. This is the interview on the designing an ATM, automated teller machine, what we call. The ATM system involves a comprehensive understanding of software architecture principles, design patterns, data structures, algorithms, UML diagrams, microservices, and cloud services. So this interview contains all about these different principles and design architectures on the ATM machine. So so there will be a detailed compilation of all the interview questions and answers covering all of these aspects to help you prepare effectively. Yeah. So let's pause it. So first question is, how would you design the overall architecture of an ATM system?
Designing an ATM system involves several layers and components to ensure functionality, scalability, security, and maintainability. So there are the high-level architecture designs we can call out. First I'll go to the presentation layer where we'll have the user interface, which handles user interactions through the ATM screen and keypad, what we use whenever we go to a ATM machine. Then second part will be of course the input validations, like it ensures that user inputs are correct and which are secure, which should be secure. Then second layer will be the application layer. Application layer is nothing but the different controller it will have. So here we'll have the ATM controller, which manages the workflow of transactions. Transactions are like withdrawal, deposit, balance inquiry, etc. Then we'll have the transaction manager, which coordinates transactions, ensuring atomicity and consistency, and security module, which handles authentication like pin verification and authorization. Third layer is service layer, where banking services communicates with backend banking systems for account management, transaction processing, etc. Then we'll have the network communication, ensures security communication between the ATM and bank servers, of course using the SSL or TLS protocols. Fourth layer will be our data layer. Data layer is the database where it stores transaction records, user data, logs, audits, etc. Then we'll have the cache, which improves performance by caching frequently accessed data. Then fifth will be the hardware interfaces, where card reader, which reads user bank cards, cash dispenses cash, the security printer prints transaction receipts. Then we'll have the secure storage, which stores cash and sensitive data securely. And the sixth layer will be the integration layer. Integration layer will have the middleware, which facilitates communication between different layers and external systems, and we'll have the APIs, which exposes services for internal and external use. Okay, and of course the key considerations will be here, scalability, which I mean through this the ability to handle increasing number of transactions day by day. Then we'll have the reliability, ensures high availability and fault tolerance. We'll have the security, which protects against unauthorized access and data breaches. And we'll have the maintainability. Maintainability is like to ease of updating and maintaining the system properly for future, right? So these are the different high level design architectures.
Okay. So here, what you said that those are good. Okay. On top of that, what are the key functional requirements of an ATM system you can call out?
Yeah, sure. So key functional requirements of an ATM system includes authentication, which of course we identify the user through card insertion and pin entry. Then we'll have the cash withdrawal, which allow users to withdraw cash up to their account balance and daily limits. Then we'll have the balance inquiry, which provide users with their current account balance. Then deposit funds, which enable users to deposit cash or checks into their accounts. We'll have the fund transfer, which allows transferring funds between accounts. Then of course we see in ATM machine also mini statement, provides a brief account statement showing recent transactions. Then we have pin change, allow users to change their personal identification number. We have language selection also in the starting, we get it, like which support multiple languages for user convenience. Then we have of course receipt printing as well, which print transaction receipts upon user request. Then we have the of course internally session management, which handle user sessions securely and timeout after inactivity. We have the error handling, of course will have manages error gracefully, and such as like insufficient funds, right, or invalid inputs, right, those to those validations. Then we have the audit and logging, of course, record which records all transactions and activities for auditing purpose. Yep, these are the different key functional requirements will be there for an ATM machine.
Cool. So of course you know solid principles, I believe. So can you talk about the solid principles in designing an ATM system?
Yeah, sure. So applying the solid principles to the ATM system ensures a well structured, maintainable and scalable architecture. So first is the single responsibility principle, which is a class should have only one reason to change. So that's the one single responsibility principle. So here in the ATM machine, like we'll have we have to separate classes for different functionalities, such as card reader, which only will read the cards, right? Then cash dispenser, through those functionality it will only be able to dispense the cash. So similarly, like transaction processor, user interface, different classes will be there for their individual functionality levels only. So each class handles its specific responsibility without overlapping with others. Second one will have the open or closed principle. So what is this? First, like software entities should be open for extension but closed for modification. Okay, so what will be there in the ATM machine, like design interfaces or abstract classes for transaction types, like I transaction, you can do a abstract class or interface here, so that new transaction types, like new things comes right now, cryptocurrency transactions, right, those kind of new level things it comes in the functionality. Which can be added by extending existing classes without modifying the core system. So we are not modifying the internal transaction types what is available today, right? What we are adding today as a cryptocurrency, that will be extending the existing class or interfaces. Of course implementing the interface, and through that we can do the according implementation. And third of the solid is LSP, which is list scope substitution principle. What is it like? Subtypes must be substitutable for their base types without altering the correctness of the program. Okay, so in ATM system, what it will be like, it ensures that subclasses like cash withdrawal transaction or deposit transaction can replace their base class, which is transaction like, right, without affecting the system's functionality, right? So we can do that. Subclasses also can be replaced with the base class without any affecting the system's functionality. So it will be as it is whenever we'll be substituting something. Okay, then we have the fourth one is ISP, interface segregation principle. So what is it? Clients should not be forced to depend on interfaces they do not use, right? So that's why the interface segregation principle comes. So in ATM machine, like, create specific interfaces for different components. Okay, for example, iCard reader is an interface with methods like read card, eject card, iCash dispenser. Sorry, this will be there, like iCard reader will have read card, eject card, so all that related to cards, right? Then we can have iCash dispenser with method like dispense cash and all, right? So only cash dispenser related things will be there. This avoids bloated interface or promotes modularity. So there is also a interface segregating is happening. So card reader will have only card related things, cash dispenser will have only the cash dispensing things parts. Okay, and last one is the dependency inversion principle, DIP. What is it? Like high level modules should not depend on low level modules, both should depend on abstractions. Okay, so mainly high level modules should not depend on low level modules, that's the major thing. So like here in ATM machine, Use dependency injection to provide dependencies like iAccount service or iLogger, like these are different interface, okay, to high level classes. Okay, so use dependency injection to provide dependencies like iAccount service or iLogger to high level classes, so that I can get those dependency injections properly. So this decouples the high level logic from concrete implementations, facilitating easier testing and maintenance. Okay, so this is very cool in like in Spring Boot and all it is having, right? Anyway, okay, so those things, yeah, these are all the solid principles we'll be using. Like I'll give you just one example here. Like in the transaction processing, transaction processor, right, high level module, this is okay. So in the high level module depends on the transaction interface abstraction, which is okay. So transaction processor is a high level module which depends on transaction interface, okay, which is an abstraction layer instead of concrete transaction classes. So I am using abstract class or interface dependency into my processing system, into my transaction processor, instead of any concrete classes. The new transaction types can be added by implementing transaction without modifying transaction processor. So if a new types added in the transaction, I can just implement it in the interface or abstract class, like in transaction, right? So my child classes or my processing system will get it by default. Okay, cool. So these are all the solid principles I can use in my ATM system.
Cool. Now we'll go to the design patterns. Design patterns provide, of course, the reusable solutions to common software design problems, right? So can you talk about something on those areas while you'll be building the ATM machines? What are the design patterns will you use, right, for flexibility, maintainability, or appropriately to implement your designs, your programs?
Yeah, sure. So several design patterns are applicable to the ATM system to address various architectural challenges. I'll start from the factory pattern. So factory pattern purpose is to create objects without specifying the exact class of object to be created. In the ATM application, I'll be doing like creating different types of transaction like withdrawal, deposit, transfer, etc. using a transaction factory. This decouples the creation logic from the client code. So I'll be having a base object like a transaction factory through which I'll be creating different transaction types. Okay. Then we'll have a singleton pattern. The purpose of it to ensure a class has only one instance and provides a global point of access to it. So in ATM machine, of course, like logging, logger will have one, right? So managing the connection to the bank's backend server of logging service or logging service, of course. For example, a logger class can be a singleton to ensure consistent logging throughput the system. So I can have a library, I can create a library of the logger, okay, of the logger for my system, from the ATM system. So from different microservices I can call that particular library of the logger, so that each microservice will use that logging mechanism. Okay. Then we can have the strategy pattern, which defines a family of algorithms, encapsulates each one and makes them interchangeable. Like in ATM machine, right, what we'll do, like implementing different authentication strategies like pin based, biometric, etc. The ATM can switch authentication mechanism without altering the core logic. I can change the authentication mechanism if I want, right? Like pin based I want, then later I want biometric, right? So I can do it without changing the core logic what is there internally. So the behavior is I can able to change through my input. Okay. So then we'll have the observer pattern, which allows objects to be notified of changes in other objects. Monitoring in the ATM, of course, the monitoring system events such as cache labels, network connectivity, or hardware status. Observers can trigger all alerts or actions based on these events, right? So it is observing mainly all the monitoring systems. What is the cache level, what is the network connectivity or hardware status, all things, and depending on that it will trigger the alert. Then we can have the command pattern. The purpose of it to encapsulate a request as an object, thereby allowing for parameterization and queuing of requests. how is it in an application of ATM? Handling user actions like button presses on the ATM interface. Each action can be represented as a command object, enabling features like undo or logging. Okay. Then we can have the adapter pattern. The purpose of it allows incompatible interfaces to work together. Right? We know the adapter, like charging adapter and all, right? Similarly here, so how is it in ATM machine? Integrating third-party software components or legacy systems with the ATM software by creating adapter classes that translate interfaces, so which directly does not support through an adapter, we can support from the ATM software. Okay. Then we can have the decorator pattern. The purpose of it, we it adds responsibilities to objects dynamically. Okay. We have in our Java only, right, different decorator design patterns, like different streaming we have, right, the IO services, IO classes, right. So similarly that here in ATM, enhancing functionalities such as adding security checks or logging to existing components without modifying their structure, so it can decorate one by one what are the different functionalities through a chain. So I am making that particular object through one by one. Okay. Then we can have the facade pattern, which purpose provides a simplified interface to a complex subsystem. The application in ATM, it be like offering a unified interface for complex operations like transaction processing, which involves multiple subsystems, authentication, then account validation, cash dispensing, etc. on this. Okay. So like in transaction creation, use the factory pattern to instantiate different transaction types based on user interface. What it was there, the transaction factory determines which transaction implementation to create withdrawal transaction, deposit transaction, etc. Right. Then this logging, authentication all will come. Like logging, of course, we told singleton pattern. Authentication is a strategy pattern, right, which authentication mechanism will be used and all. So this way we can make it more modular, extensible, and easier to manage. Yeah, that's all from here.
Cool. So, of course, you know the data structures and algorithm, it looks like. So, what data structures would you use to manage ATM transactions and why?
Yeah, so here managing ATM transactions efficiently requires selecting appropriate data structures to handle various operations like transaction logging, user sessions, and resource management, right. Like in queue, right, managing transaction request, so there might be long queue, right. So a queue follows the first in first out FIFO principle, uh, ensuring that transactions are processed in the order they are received, which is essential for maintaining consistency and fairness. So all the orders or transaction will come through a queue, right. So we'll be using queue here, right. Then stack design patterns, I mean the data structures. So here the use case will be implementing undo functionality or tracking navigation history within the ATM UI. So the reason is a stack follows the last in first out LIFO principle, allowing the system to revert to the previous state or screen when needed. So through the undo, like I can go to the previous action. Then third, like hash table, on the dictionary one, the use case will be storing and retrieving user account information quickly. The reason is provides constant time complexity of big O of 1 for insertion and lookup operations, ensuring rapid access to user data based on account numbers or card IDs. Then we'll have the linked list. Use case for using linked list is like to manage a list of active sessions or queued hardware requests, so which allows mainly efficient insertion and deletion of elements, which is useful for dynamic session management here. Then we can use the BST, binary search tree, or balance tree. Balance tree is like AVL or red black tree. The use case of these are organizing transaction logs or account data or for efficient range queries or ordered traversal. Reason of this is like to enable efficient search, insertion and deletion operations, which might take a big O of log n time complexity, which is beneficial for maintaining sorted data. We can use the graph use cases like representing network connections or dependencies between different system components. The reason to use graph like facilitates the modeling of complex relationships and interactions within the ATM network or between microservices. Then of course array list is very compulsory nowadays in each software, like it use cases storing fixed or sequential data such as predefined menu options or configuration system settings. Like of course then the reason we can use provides easy access to elements by indexing, which is useful for static data storage. Yeah, so these are different data structures we can use on this. Yeah, like of course we talked about transaction queue will be using, like where we'll be using the queue for first in first out, right? Then of course the queue we are using, then hash table we are using, right, where the key is the account number, where and enabling quick retrieval of account deleting account details during transactions, right? Then for session management we are using linked list, right, where we as object we can keep the session to handle active user sessions, right, efficient addition or removal of users. Then of course the searching has hash based lookups, right, for the constant time access. Then for the sorting we can use the quick sort, merge sort, right. Then for organizing transaction logs if necessary here, right. Concurrency ensures thread safe operations on shared data structure, especially when handling multiple simultaneous transactions or sessions. So by carefully selecting and implementing appropriate data structures and algorithms, the ATM system can achieve high performance, reliability and scalability.
Cool. So on the UML diagrams, when you go, so like the UML is the Unified Modeling Language, right? Diagrams are very essential for visualizing the system's design and architecture, right? So what UML diagrams would you create for the ATM system, and what would they depict?
Yeah, so creating UML diagram helps in visualizing, specifying, constructing and documenting the system's architecture and design. For an ATM system, the following UML diagrams are pertinent, of course required, right? So first is the use case diagram. So the purpose of it is, first it illustrates the interactions between users here actors and the system. So it depicts like actors such as customer, bank server, maintenance staff, etc. And use cases like authenticate user, withdraw cash, deposit funds, check balance, print receipt, etc. Then these are the use case diagram. This will come under the use case diagram. Okay, then we'll have the class diagram, uh, which shows the static structure of the system, including classes, attributes, methods and relationships. So classes like ATM, transaction, account, card reader, dispenser, then receipt printer, etc. And relationships like such as associations, then the inheritance will be there, right? Like withdrawal transaction inherits from transaction, and of course the dependencies will be mentioned here. Then we'll have the sequence diagram. Details of this like details of the all the it details the interactions between objects in a particular scenario over time. The sequence of operations for a typical withdrawal transaction, including user input, authentication, account verification, cash dispensing and receipt printing. So end-to-end flow of one particular object life will be mentioned here in the sequence diagram. Then we'll have the activity diagram. The purpose of it represents the flow of activity or processes within the system, which depicts the workflow of various operations like transaction processing, error handling and user navigation through different menu options. Then we'll have the state diagram, which shows the states of an object can be in and how it transitions between states based on the events. So and it depicts states of the ATM such as idle, card inserted, authenticated, processing transaction, dispensing cash, ejecting card, etc. Then we have the component diagram. The purpose of it illustrates the organization and dependencies among software components, which depicts components like user interface, transaction manager, security module, backend services, hardware interfaces, etc. And then we'll have the deployment diagram, which describes the physical deployment of artifacts on nodes. So here hardware nodes like ATM machine, bank server, network infrastructure will be there, and software artifacts deployed on each node is nothing but a machine, a compute machine will have a node, right? So like our Kubernetes or right, so those will have the nodes, something like that, just like a think as a server, right? Such as the ATM's application on the ATM machine and database servers on the bank server. Then we have the communication diagram, similar to sequence diagrams, but focuses on the relationships and interactions between objects, such as like the communication between customer, ATM, bank server. So these all communications between this and other components, of course, whatever are involved during a particular transaction. So all this will be mentioned on the transaction level of between different objects. Cool. I'll just give an example of a sequence diagram for withdrawal, maybe, so that it will give a clear idea. So like customer inserts a card, ATM requests a pin, customer enters a pin, then it goes to ATM, sends authentication request to bank server verifies credentials, then ATM prompts for withdrawal amount, then customer enters amount, next ATM requests cash from cash dispenser, then cash dispenser dispenses cash, then ATM updates account balance via bank server, then ATM prints receipt, next last is customer takes cash and receipt, right? So by utilizing these UML diagrams, developers and stakeholders can gain a clear understanding of the ATM system's architecture, behavior and interactions, facilitating better design and communication.
So how would you decompose the ATM system into microservices?
Yeah. So decomposing the ATM system into microservices involves identifying distinct functionalities that can operate independently while communicating through well-defined APIs. Okay, here's I'll give you a few decompositions on the different APIs. So first service will be like authentication service, right? So which handles user authentication, including PIN verification and session management, which mainly the responsibilities will include like validate user credentials, manage authentication tokens, handle multiple multi-factor authentication if required. The next service will be the transaction service, which manages all types of transactions such as withdrawal, deposits and transfers. The responsibilities will be processing transaction request, ensure transaction integrity, then update account balances, etc. Then the third one will be account management service, which manages user account information to retrieve account details, update account information, handle account creation and closure. Fourth will be cash management service, to oversee the dispensing and dispensing of the cash in the ATM, which monitors cash levels, control cash dispenser hardware, schedule cash replenishment, of course mainly the like when it is getting withdrawn or added, right? It is maintaining that level. Then we have the receipt service, which manages the generation and printing of the receipts. It formats receipt data interface with receipt printer hardware. Then we have the logging and monitoring service, logs system activities and monitors system health, which collect logs from various services, then monitor performance metrics, alert or anomalies. Then we have the notification service, which handles notifications such as alerts to maintenance staff or sending emails or SMS to users. Then we'll have the send real-time alerts, manage notification preferences. Then we'll have the interface, like hardware interface service, which interfaces with ATM hardware components like card readers, cash dispensers and printers, which communicate communicates with hardware drivers, handle hardware events, ensure secure interactions. Then the next service will be reporting service, which generates reports for auditing, compliance, and business intelligence, which aggregates transaction data, create financial reports, support data analytics. Then we have the security service, which ensures the security of the system. Uh, then it manages encryption, handles security policies, perform vulnerability assessments, etc.
Okay, now let's go towards microservices design patterns. Can you talk about what microservices design patterns would you use for creating this design?
Yeah, so design patterns applicable to microservices in the ATM system can be this way. Uh, so API gateway is required where it acts as a single entry point for all ATM functionalities, routing requests to appropriate microservices. Then we'll have circuit breaker pattern, where it prevents system failure by isolating failing services, ensuring the ATM remains operational for other services. Then we should have the database per service. Each microservice, where like transaction or account services, manages its own database to reduce coupling. Then we'll have event driven architecture, where it enables communication between services through events, such as publishing a transaction completed event for the notification service. Then we should have retry pattern, which ensures reliability by retrying failed operations, such as reconnecting to the bank's backend in case of network issues. We should have service discovery, which dynamically locates microservices, ensuring seamless scaling and fault tolerance. Also, I think we should have saga pattern, which handles distributed transactions by breaking into smaller and independent transactions coordinated through multiple events. So these are very critical design patterns under the microservices we need to have, definitely. Yeah, that's, I think that, yeah.
Okay, cool. Regarding cloud services, when you talk, what cloud services would you use for the ATM system?
Yeah, sure. So cloud services can enhance the scalability, reliability, and security of the ATM system. Like the services will be using compute, of course, where if we talk about the AWS cloud service, right? So EC2, the compute. Then, or if we talk about Azure, so Azure Virtual Machine, or Oracle, if we talk Oracle Cloud Compute for hosting the backend services. Similarly, for storage, of course, AWS S3 or Azure Blob Storage, or you can talk Oracle Object Storage for storing transaction logs or receipts or reports. Then we'll need to have database, of course. For banking, right? So this is RDS, relational database, of course, where AWS RDS, they, or Azure side it is SQL database, or Oracle Autonomous Database, right, in from OCI, for managing account and transactional data. Then we need to have authentication mechanism, where AWS Cognito or Azure Active Directory or Oracle Identity Cloud Service for secure users authentication. Then event streaming, like Kafka or AWS has SNS or SQS, or Azure Event Hub for event driven communication. Then we need to have monitoring service, so where we have AWS CloudWatch or Azure Monitor or Oracle Management Cloud for tracking system health and performance. Of course, on the networking perspective, load balancers and VPN to manage traffic and secure communication. And finally, we need to have anyway disaster recovery, like multi-region deployments and backup services for high availability. So these are the high level few must have the services. Yeah, I think that's it from my side.